welcome back. In the previous lecture, we completed our discussion on the liquid drop model. In this lecture, we will begin our discussion on another important model uh, to describe the properties of nucleus. The second model that we are going to be discussing is called the nuclear shell model, and we will motivate this model in this lecture. There are many isotones when the number of neutron is about 50 and when it is about 82. The liquid drop model is not able to explain why there are so many isotones for some specific n. There are also many isotopes when there are even number of nucleides. For example, when there is even Z, there are more isotopes. Again, liquid drop model fails to explain this. The most important aspect, which cannot be explained by the drop model and which is very critical to understand the properties of nucleus, is the presence of magic numbers. That means there are some specific atomic numbers and atomic weight wherein the nucleus is much more stable compared to the atomic number and atomic weight in the vicinity. So what makes them more stable is not clear within the liquid drop model. So because of this fact, there are other consequences, alpha decay and beta decay, that tends to lead to the formation of magic number nucleides become more favorable. Likewise, if you can absorb a neutron and form a magic number nucleus, then the neutron absorption cross section for those reactions also is higher. The liquid drop model is not also able to explain the separation numbers of magic number nucleus, why it takes much more energy to remove the highest energy neutron or highest energy proton from magic number nucleus. That's not explained by the liquid drop model. And uh, there are other observations, like the heaviest stable nuclei is bismuth with uh, atomic weight, atomic number, and this many neutrons. Why this should be so is not clear. There are some excited states that are formed because of beta decay. This release neutron much more easily, which suggests that the last neutron is loosely bound from in these excited states. It is not possible to rationalize these observations within liquid drop model. So these are some of the important observations that came from experimental studies that motivated the motivated the way to model the nuclear properties via a model which is used in describing the properties of electrons in the atom. So this model of shell structure is not something new to sciences. Shell structure has been very powerful in explaining the properties of electrons in the atom. So even though liquid drop model had a lot of successes, because of these observations, a model that was used for describing the properties of electrons in atoms was extended to model the properties of nucleons in the atoms, in the nucleus specifically. So, what is the central issue here? The central issue, in a way, is about magic numbers. Why are some atomic number and atomic weights favored, right? For example, if the atomic number is the following, or if the number of neutron has these values, then such nucleus is much more stable. So if you look at this feature from the context of electronic structure, there is a close analogy, right? There are closed shell configuration in noble gases with these electronic number of electrons, wherein the electronic structure is very stable, right? So at that time, when there are a lot of observations which were beyond the liquid drop model, there was an appeal to the model of the shell model, which was very effective in not only rationalizing this feature, many other features, certain periodicity and reactivity, those could be very well explained by the shell structure. So there was an appeal to this model to see whether that can be extended to the nuclear structure to explain many of the observations. Right. What kind of observations? Observations related to spin and excited states. We will see more elaborately what we mean by this, and observations related to parity. Parity may appear slightly more complicated, but you are aware of parity from your high school. For example, if you look at the atomic orbitals, there's the s orbital and 2s orbital, p orbital, and so on. What do we mean by parity? Certain wave functions have certain symmetry. That is, if, for example, if this is the z-axis, if you go from minus c to plus c, the sign of the wave function is opposite, right? So the sign of the wave function becomes negative. So such kind of wave functions have certain symmetry properties which arise due to certain fundamental reasons. And these are very consequential in many ways. So it is important to explain why parity is important and so on. So within the liquid drop model, there's no way to explain these issues. So these orbitals, by orbital, I mean the wave function for an electron. That is what is called atomic orbitals in the context of electronic structure. So orbital in general means wave function for a single particle. That's what we mean by an orbital. So this orbital structure in the electron arise because of the electrons feel potential that is presented by the positive charge of the nucleus. So there is a central potential of particular symmetry. In this case, in the case of atoms, it is spherically symmetric. And this potential offered by the positively charged nucleus felt by the electrons leads to the quantization of the energy levels of the electron and the nature of the atomic orbitals. So there is a central potential that is obvious in the case of nucleus and the potential felt by the electron. However, when you are thinking about nucleons, okay, it is not clear what is the potential felt by the nucleons. There is nothing in the center of the nucleons that seems to offer any potential which would lead to the energy levels felt by the nucleons. or lead to the wave functions of the nucleons, right? This is the orbitals for the electrons, which is um, obtained because of the quantization using this potential. However, it is not clear what is the potential that we should be using for nucleons. We will look at this later, even though we have sort of hinted what might be the potential. We have seen that there are this strong nuclear forces that are felt by both protons and the neutrons, which offer a confining potential, a strong confining potential. Um, that is a possibility, but that potential is quite different from the potential offered by the nucleus to the electrons. So let's also contrast the liquid drop model against the nuclear shell model. Liquid drop model suggests strong interactions within the nucleons, because of which the nucleus behaves like a condensed matter. There is something like a nuclear matter which offers collective behavior, collective oscillations. So when you have condensed matter like normal liquids and solids, there are no collisions. There is no particle motion leading to collisions. These collisions characterized by mean free path is suggestive of gases, right? So in let's say gases, even even without considering ideality of gases, you can think about certain trajectory, mean free path, and uh, and collisions. So in gases, particles can move independently of the other particles. However, in liquids, independent movement is not possible because each particle is always in contact, or there is a coordination sphere with other particle. Each particle is in contact with other particles. So a trajectory which is independent of other particles is not possible. So these two are very different. This seems to liquid drop model is suggestive of condensed matter. This nuclear shell model, you will see, is suggestive of low density gases. So both these models you would see are going to be very effective in explaining observations. We have already seen the effectiveness and the power of liquid drop model. You will see in the next few lectures why nuclear shell model is very powerful. So how do we rationalize the two very different physical situations? In this model, the nuclear matter seems to be condensed matter. In this model, it seems nuclear matter seems to be low density gases. How do we reconcile both these models? This has no collision. There are collisions here. So there is a need to resolve the contradiction. So if you think about the collisions in, let's say, a low density gas, the collisions involve momentum transfer and lead to rearrangement in the energy levels of particles that undergo collisions. So when there is rearrangement of energy levels, so there can be, let's say, excitation of one of the particle to some excited states because of collisions and so on. So this is very critical. That is, collisions leading to rearrangement of levels is intuitive and central feature of collisions. However, the nucleons are fermions obeying Pauli's exclusion principle, right? What does that suggest? Each level um, cannot be filled by more than one particle, right? So in your high school, you might have seen of Pauli's exclusion principle, wherein you would have heard that no two particles, in that case of electrons, can have um, all the same quantum numbers, right? So in a way, the phase space or the space wherein one electron can reside is different from the space resided by any other electron, right? So that's the meaning, the physical consequence of Pauli's exclusion principle. So this has um, consequence to reconciling these two features. So if the levels are occupied, collisions are suppressed, right? Because if collisions lead to rearrangement of levels, uh, if the levels are occupied, collisions are suppressed because there is no way a collision can lead to rearrangement and occupancy of a level that is already occupied, right? So occupancy of pre-existing levels in a way suppress the collision. Therefore, while the collisions might be important at the edge of occupancy, see, supposing we have um, tiers wherein these levels are occupied, in the inner levels, all these levels are occupied by particles. Only towards the edge of occupancy or towards the outer levels, there can be vacancies, right? So these collisions might be important at the higher levels, but the inner levels, and in the inner levels, the collisions might not be the operational mechanism for rearrangement of levels. So if there are questions, we can discuss this in the class, but this feature of Pauli's exclusion principle is very, very critical for the suppression of collisions. So in the next lecture, we will look at what is the potential that can be utilized for the nuclear shell model, and because of which, what kind of states might arise in the nuclear shell model. That's the topic for the next lecture. Thank you.